Yes, so the floor is yours, Chenhao.
Sure. Hello, everyone. Good morning, I guess, for most of us, and good evening if you are in China. Today, I will introduce the last part of our crash course lecture series, which is on both urban climate monitoring and urban climate modeling. For modeling, I will introduce both physical models and scale models and also numerical models. And also the content I will introduce in today's lecture is largely adapted from both Oak's Urban Climate book and also a few other resources like literature and some of my previous research experience. Okay, let's get started. So when we ever want to carry out an urban climate research project, there are some basic things we need to have in mind first. First of all, we need to be clear about what kind of properties or processes of interest we're trying to understand. And also we need to be clear about the physical extent or, for example, spatial extent of the system we are considering. And the last one is, what kind of strategies are available out there for us to capture the spatial and temporal variations within this, urban system. So this spatial can be, both horizontal and also vertical. So 2-dimensional or 3-dimensional even. So urban climate observations, first of all, can be broadly classified into two types. One is the so-called instrumented stations, which can provide us long-term routine urban meteorological informations. This kind of instrumented stations are also commonly used for weather and climate monitoring. And here are a few examples I have. The first graph here is a rooftop weather station. You cannot see my cursor. So a rooftop weather station in New York City operated by New York State Mesonet. We see a rain gauge over here. And also this one is an automatic surface observing system or ASUS station in an airport in Nevada. And this website is basically where NOAA is hosting all observation data from ASUS or AWOS stations. So these AWOS or ASUS stations are sort of the standard observational data commonly used in many weather and climate-related studies beyond the urban climate itself. So the second type of observation is field campaign or field experiment, which is commonly used to evaluate some, long-term, to evaluate some certain aspect of the urban climate. These field campaigns usually have much shorter time when compared with these instrumented stations, but they have much denser spatial configuration. Usually we will have like a very densely a configuration of sensor network, for example, across the neighborhood, or for example, for across the entire city, just to figure out, the distribution of air temperature or the distribution of air pollution after like a tracer release, which we will talk about this in a moment. There are generally 3 different types of field campaigns, depending on what kind of instruments you are using. The first one is, of course, the fixed stations, similar to what we have for AWOS or ASOS stations, basically similar to these routine measurements. But the difference here is that these stations we are setting up for field campaign will only be there during the experiment and might be removed afterwards. The second type is, of course, the mobile measurements. We can, drive the car around them, carrying a set of sensors with us to poke around the 2-dimensional distribution. And of course, the third one is a so-called flow following, and we might release a balloon, tethered or untethered balloon, and also we can have other, instruments where, like for example, airborne aircraft measurements, so that we can get a better understanding of the 3-dimensional distribution of some atmospheric variables. So when we talk about the instruments and sensors commonly used for urban climate observations, we can also classify them into 2 different categories. The first one is the in situ measurements. Of course, these are measurements taken in the same place. The phenomena are occurring with our sensors fully immersed in the media of interest. In this case, where immerse our sensors within the atmosphere, within the moving air. Think about if you are measuring the water temperature, you must immerse your sensor within the water, right? And the second type is remote sensing instruments. They are obtaining information about the properties of an object from a distance. So we do not make any physical contact with the object. So one particular remote sensing instrument is the radiometer, which we are measuring radiation. We cannot just we can I mean radiometer is a typical remote sensing instrument. So before we introduce different types of instruments, I do want to spend a few minutes to give you a brief overview about the urban surface energy balance. So almost all properties or all phenomena we are measuring in the environment of in the urban environment are really highly related to surface energy balance. Or broadly speaking, I should say this is not limited only to urban climate, but for all kind of land surfaces, all properties we're measuring are highly relevant to the surface energy balance. So this within the field of surface energy balance, there are mainly four types of energy or heat exchanges between the land surface and above atmosphere. So the first one is radiation, and all materials will emit energy as electromagnetic waves, which is a function of temperature. And as long as your object or materials has a temperature higher than absolute zero, which is 0 Kelvin, it will emit radiation at some certain wavelengths. And as this radiation travels across the space, it will interact with materials, and this radiation, incoming radiation, will be partitioned into the scattered radiation, reflected radiation, absorbed radiation, and transmitted radiation. And the summation of these four portions should be equal to 100%, which is equal to the incoming radiation. And in the surface energy balance measurements, we commonly call solar radiation as shortwave radiation. This is mainly because the distribution of the peak radiation from the sun is distributed within a band from wavelengths 0.1 micrometer to 3 micrometer. The peak is around 0.5 micrometer, and this is the essential driver of the Earth's climate system. And the second one, when we are thinking about the radiation emitted from the Earth and atmosphere, which is a sort of an integrated system with an equilibrium temperature of 15 degrees Celsius, I would say. And we call this part of radiation as terrestrial radiation or long-wave radiation. It has a wavelength band from 3 micrometer to 100 micrometer. And the peak is around 10 micrometer, which is well within the infrared band. So the second type of, or second term within this urban surface energy balance is this so-called conduction, which is essentially the diffusion of heat or like thermal energy within one material or between two materials in contact. And heat conduction is the main form of heat transfer in solids. So this is also, determined by the second law of thermodynamics. Basically, the heat is always moving from the hotter objects to colder objects, and this conduction is also the cause of ground heat flux in the urban environment, or like sometimes storage heat change in the urban environment. So the third one is convection, which is the transfer of heat due to the movement of fluid. So of course, this is the main form of heat transfer in liquids and gases. It is due to the movement or the motion or mixing of fluid, which can be much more effective when they are moving fast. And this is also the cause of sensible heat flux or turbulent sensible heat flux, sometimes we call them. And this sensible heat flux means the heat exchange, that can really change the temperature of an object or a material. And this convection is much faster than molecular diffusion motions of molecular diffusion, and it is highly relevant to the speed or the velocity of eddies that are moving within the turbulent flow. And the last one is phase change related surface energy. So this phase change means the heat exchange due to either evaporation or condensation or any other kind of conversion between the different phases of water, liquid, solid, and gaseous. And this phase change related energy is called latent heat flux, and we call turbulent latent heat flux sometimes. And it is also governed by air mixing. But one particular characteristic of this latent heat flux is, during phase change, the temperature of the solid, or like a mixture of solid and liquid, or a mixture of liquid and gas, the temperature will not change, but we are either consuming or absorbing energy. So there's energy embedded within this phase change process. So based on the first law of thermodynamics, we must have a conservation of energy across the entire system, right? So if we think about a highly simplified urban surface, we treat this three-dimensional complex urban surface as a black box. We have input within the system. We also have output. So input must be equal to output. So in this case, we can write this simplified urban surface energy balance equation. On the left-hand side of this equation, we have Q star term, which is net O wave radiation. And this net O wave radiation is essentially the summation of downwelling short-wave radiation from the sun, downwelling long-wave radiation from our atmosphere, minus the upwelling short-wave radiation reflected by our ground surface, and minus the long-wave radiation emitted from the ground surface. And on the right-hand side, we also have this, Q star term decomposed into three major terms. QH is a sensible heat flux, QE is latent heat flux, both are turbulent heat fluxes, and QG is ground heat flux. And in practice, the measurements of this, turbulent heat fluxes heavily rely on some high-frequency wind measurements. I will talk about this in a moment. So here are some commonly used instruments and sensors for atmospheric measurements, and these are not limited to urban environment. We can actually use most of these instruments and sensors in any kind of ground surface, or even above the aquatic system, as Dr. Lee introduced in one of our former lectures. So first of all is this thermometer. We use thermometer to measure temperature, and sometimes you see a thermometer surrounded by this kind of ventilated shelter or shield, which can make sure the temperature we're measuring is in equilibrium with the air. And we also have this hygrometer, which gives us the reading of humidity, and we can use barometer to measure pressure. And of course, these two are sort of outdated. Now we have some more advanced sensors to measure humidity and pressure. And we also have this radiometer. This one is a typical four-way radiometer, which is using this pyrometer to measure the long-wave radiation, both upwelling and downwelling. And also this use this pyrometer to measure downwelling short-wave radiation and upwelling long-wave radiation. So this one is for long wave, this one is for short wave. So we can use these two sensors to derive the Q star term. We know the upwelling short wave and long wave, and downwelling long wave and short wave. We can reasonably derive this term over here. Okay, so we also use this rain gauge tipping bucket to measure the rainfall rate. And this instrument basically has two connected buckets. It will tip over once one of these two buckets collect enough water, liquid water, I mean. And we also have this integrated soil sensor, which can measure the soil moisture, soil temperature, and soil conductivity, and also all other different kind of soil properties. This one is a commonly used wind sensor. It can give us the wind speed, wind direction. Wind speed is from anemometer, and wind direction is from vane. But this kind of measurements are a low frequency. It cannot give us a proper measurement if we want to get an understanding of the sensible and latent heat flux. So this is why researchers developed this sonic anemometer, which can measure the high frequency three-dimensional wind speed. And using this three-dimensional wind speed, we can also derive the wind direction. And this kind of instrument uses the ultrasonic sound wave to determine the instantaneous wind speed. This is only possible because it measures the the impact of the wind passing by this sonic anemometer, and the impact of the wind will impact the sound waves traveling between these different pairs of transducers. And because we have wind traveling through, the sound wave can be either speed up or slow down. We can measure the change of their speed to determine the three-dimensional wind speed. So if we, in the field, we must put all these sensors together. So this is a typical setup of a flux tower in the field. Of course, we need to put everything on a tripod or like a flux tower. So this is something Neon has. So we have this, the steel or like a metal structure. We can put multi layers of sensors on top of that. But a more commonly used structure is something like this too. We have this a tripod about 3 meter or 4.5 top in height. And we can either put it on the ground surface or on a rooftop. You will see one of the rooftop measurement examples in one of my following slides. So of course, if we want to measure the temperature, relative humidity, we have this thermometer, hygrometer set up on this tower. We also have this radiometer to measure the radiation. We have this soil sensor and rain gauge at the bottom, but we also need a data logger so that we can temporarily store our data. And in the field, we often do not have a power outlet, so that's why we also need a solar panel to power up the entire system. And one thing you might notice is that here, in addition to the sonic anemometer, we also have this unique structure. This one is an open pass carbon dioxide and or water vapor analyzer, which can be used to measure this carbon dioxide concentration, water vapor concentration. And when we combine these two sensors, we can derive the latent heat flux and also the carbon dioxide exchange between the land surface and the above atmosphere. And sometimes we might also have this more expensive instrument. This is an open pass methane analyzer, which can also help us get an understanding of the methane exchange between the land and the atmosphere. So among all these sensors we use for measurements, radiometer is actually quite different because it is a typical remote sensing instrument, as I mentioned previously. It can measure different radiation components only because it is very sensitive to energy associated with radiation. These also, based on how a sensor works, we have both active remote sensing instruments and passive remote sensing instruments. So active remote sensing instrument, they can actually generate a beam or like a sound wave and record the depleted beam or wave due to the object or medium. And the passive remote sensing instrument is that it can only report the absorbed or reflected radiation. For example, this radiometer is a typical passive remote sensing instrument because it is not emitting beam for measurements. Well, in addition to this radiometer, we also have a whole variety of different remote sensing instruments that we can use for urban meteorological or climate observations. For example, we have this, radar, where the full name is radio detection and ranging. Radar, tracks the suspended materials using radio wave. And this one is a typical WSR 88D, which is the so-called weather surveillance radar. It's a Doppler radar. This one is on oil campus, and it can measure, the airflow or the aerosol distribution, cloud and precipitation, based on some certain, wavelengths. And this one is a SODA, which is based on sonic wave. It's based on a sound wave. It can be, it is commonly used for atmospheric boundary layer wind profiling. And we also have this very simple, thermal camera. I think this one is from FLIR, and it is based on, infrared radiation. And this one is LiDAR, based on, light profiling. It can give us the atmospheric boundary layer profiles using, this monochromatic laser. Basically, we only have the beam within a single wavelength. And the last one is the so-called scintillometer, which can give us the area average fluxes using monochromatic laser. And this one, must have this set of receiver and transmitter. So this receiver is emitting a beam, and it will be received by the transmitter. We can measure the strength of this beam to determine the fluxes. And among all these different remote sensing instruments, this one is of course a passive one, and this one is also a passive remote sensing instrument. But all these four different kinds of remote sensing instruments are active remote sensing instruments because they are emitting their signals on themselves. Okay, now we learned different types of sensors and instruments. Let's put this into context. So let's imagine we have a thermometer at a height of 2 meters above the ground surface, which is located within a very homogeneous grassland. And because considering the relative height of this thermometer, we can consider that this thermometer is well within the internal boundary layer generated by this grassland. And the sensor, the reading we have from this thermometer, the temperature we're measuring, is actually, it is measuring the turbulent eddies that are passing through it, which can be, either warmed up or cooled down by the upwind surfaces. So with steady wind coming from this direction, we can reasonably assume or infer the surface area that is generating the monitor signal. In this case, is temperature. This area is usually this elliptical shape. We call it a footprint, or source area. Or although sometimes you might see more rigorous definition, footprint actually means the function of this elliptical source area. But here we use footprint and source area interchangeably, just for simplicity, just to be concise. And there are a bunch of different variables or like conditions that can influence the size and shape of the footprint or source area. As you can imagine, if we have like a more complicated surface area, the footprint can also be different. Of course, if we have changing wind direction and changing wind speed, this elliptical shape can also change. And the shape and size is also dependent on the atmospheric boundary layer stability condition. For example, we will have totally different shape or size of the footprint under stable condition versus unstable condition. So now think about a slightly more complicated condition. If we have a mixture of cool grass and hot pavement, something like this, and under different wind direction, the thermometer is actually collecting different composition of the source area, signals from this different composition. And for example, if the wind is from this direction, we are measuring a signal from this cool grass. And if it is coming from this direction, we are measuring signal from this hot asphalt. But for this one, it will be a mixture of both. So this actually means that what we're actually measuring at the sensor can be largely controlled by the advection or by the wind speed and wind direction. This is especially the case when we are putting our sensor within the complex urban environment, because the sensor, if it is close enough to the ground surface, it will also be surrounded by a bunch of vertical surfaces like walls or other building infrastructure. Now we know that the signals we are recording at the sensor location is largely determined by a source area. If our goal is not only measuring the a relatively small surface area, but instead we are trying to measure the influence of an urban neighborhood on the local climate condition, we must also take into account a few other factors. So think about what if we have this urban neighborhood with a prevailing wind blowing from the left, and the roughness elements within this urban neighborhood will generate an internal boundary layer, something like this. Is like this visualization in the water tank. So in order to have our measurements really represent this neighborhood, we must make sure the sensor is well located within this internal boundary layer. Also, we must think about the influence of individual roughness elements on the measurements we get at the sensor. So we must make sure that sensor should be located well within the inertial sublayer, which usually a rule of thumb is that the sensor height is at least 1.5 or 2 times the mean height of the building. So in this case, the sensor will be well above the roughness sublayer, but still within the surface layer of this, urban boundary layer, so that it will not be influenced by individual roughness elements. Instead, it is measuring the integrated effects of the underlying buildings. And well, here are also two related concepts. This leading edge is basically the windward edge of the the very distinct boundary layer generated by this surface. The fetch is basically the distance between the sensor and the leading edge generated associated with this unique urban neighborhood. So another way to look at the source area is this two-dimensional plan view I'm showing here. So this is the top view of this distribution of source area. The shaded isoplex in this graph represent the relative contribution of the measured signals to, as the sensor. Also, as I mentioned, previously, the boundary layer, atom-fact boundary layer stability condition can also influence the shape and size of the source area. So in this case, I'm using one example from one of my previous studies done in West Phoenix. We are trying to understand the source area of a flux tower in West Phoenix. And the red shaded area is 90% source area. And the blue one is, I think I don't have the label here, but I think it's 50%, either 50% or 30%. But basically, you can see there is large difference in terms of the size and shape of the footprint or source area during daytime versus during nighttime. Both are in spring. This is mainly because during daytime we have much more unstable atmospheric condition, but at night the atmosphere is more stable. And this shape and size can be largely influenced by these conditions. Also, the source area is highly dependent on measurement height, as I mentioned previously. And a rule of thumb is that the ratio of height to source area is usually 1 to 100. For example, if we have a flux tower set up at a height of 10 meters above a very homogeneous surface, the source area will likely have a size of around 1 kilometer because the ratio is 1 to 100. So compared with this turbulent source area, the source area of a radiometer is much simpler. So if we have a radiometer facing downward toward an urban neighborhood, similar to our bare eyes, the area that is seen by the sensor is more like a hemispherical view. Basically, for elements that are closer to the sensor, we mainly see their, these horizontal surfaces. While for elements located a bit far away from the sensor, we're seeing these, these vertical surfaces, just like this oblique view. This is especially the case if we are using a thermal camera to measure some surface temperature of an urban neighborhood, because when the sensor is pointing, toward only a portion of this urban neighborhood, we might see large variations in terms of the surface temperature we measure over this vertical surface, especially walls. When the position of the sun changes, when we have different solar elevation angle, the radiation reflected by this vertical surfaces can also largely change. So, for example, a shaded wall in the morning may reflect solar radiation in the afternoon. And this large variation we measure from a thermal camera will create a lot of potential biases. These biases are often referred to as the so-called thermal anisotropy. You might see this word often in the field of urban climate literature. So now we know how different sensors can have different source areas. Turbulent source areas has this typical elliptical shape, while radiation source area, if it is facing downward, has this more regular shape. So if we have a flux tower set up in an urban neighborhood, there's a source area mismatch between the turbulent heat flux measurements and radiation measurements. We're sensing, signals from different portions of this neighborhood. This is actually one of the reasons why we cannot really achieve surface energy balance closure in the field. Okay, let's go through some, commonly used platforms for urban climate measurements. So these platforms I'm showing here use different sampling approaches. They can be, either there's fixed stations across different scales, flow following techniques also across different fields from urban canopy layer to surface layer to urban boundary layer, and also mobile measurements. We have ground-based mobile measurements, but we also have this aircraft or drone-based measurements. We even have satellite measurements. So they also have this these different measurements heights, so which will reflect urban climate signals at different spatial scales. And of course, satellite has a different revisit time, which will also have different temporal scales. So close to the ground surface, we have the most commonly used fixed station measurement. Here are a few examples. This one is a temporary site to measure pedestrian thermal comfort. The two in the middle are actually monitoring stations to measure urban micro-meteorological conditions over different surfaces. So this one is set up on Princeton campus. This one is in Phoenix, right next to ASU campus. And the last one is just an integrated weather station or so-called smart station installed on a light pole in urban environment. So this is like some more advanced or like cost-effective measurement technique commonly used in cities. However, if our goal is to measure the local scale conditions, the sensor should be at least 1.5 or 2 times the mean building height, right? As I just mentioned. Preferably, the sensor must be located within the initial sublayer or like a constant flux layer. And here are a few other examples. Usually, in densely populated cities, we tend to have a rooftop station, just something like this, or like this one on University of British Columbia campus. And it's okay as long as the sensor is well above the roof, but it can be tricky if the sensor is very, very close to the roof, like this one. Because the sensor will likely pick up some signals from the roof instead of the urban neighborhood. It is not representing the general conditions of the surrounding urban neighborhood. So if we want to measure the entire urban boundary layer, we need very, very tall towers, at least beyond the lowest 10% of the atmospheric boundary layer, so that we are above the surface layer. We are now within the mixed layer. Here is one example showing one of the highest urban flux towers in the world. This multi-layer flux tower is managed by Institute of Mass and Physics, or IAP, in Beijing, China, which is over 300-meter height, and it has this 15-level meteorological measurements and also 7 different turbulent flux observation systems. So this tower can be very, very expensive, but it's also very unique. So compared to these fixed station measurements, the central idea of the mobile measurements is that we can move sensors through the atmosphere to get a sense of the spatial pattern. So mobile measurements are usually also called transverse measurements. We can use this to measure many variables, but wind is a no-go because sensor is moving around all the time. So we are not measuring the actual wind speed. We are actually have this compound effect from this movement of sensor itself. And this kind of mobile measurements can, either supplement the fixed station measurements, or it can also, be purely designed to give us a two-dimensional measurements or map. But sometimes we also need to correct the measurement data because, sometimes we need to consider the elevation induced temperature variations or some background warming or cooling during the entire measurement campaign, because these mobile measurements can usually last for a relatively long time. And also, we also need to consider the potential contributions of traffic to measurements. Sometimes, if the vehicle stops, it will be influenced by the waste heat emitted by other vehicles nearby. So mobile measurements are also commonly used to probe the entire urban boundary layer. We can use aircraft or drone measurements to get a three-dimensional pattern of some atmospheric variables. We can also use balloon measurements to get vertical profiles, which are of course much more economic when compared to this very expensive aircraft the world is strong. And this balloon they will they have like a sensor attached to them. They will transmit the monitoring data back to the receiver. We also have these flow following techniques. I would actually consider these techniques a special form of mobile measurements. We can use some buoyant visual markers like smoke or balloon to track the motion of the air or eddies. Sometimes we can also release some artificial non-reactive compounds or so-called tracers to mimic the emission of pollutants. So this has been done in both the Urban 2000 field experiment in Salt Lake City and also the joint Urban 2003 field campaign in Oklahoma City. And here you see this two-dimensional distribution of tracers measured by different sensors. So the last platform I want to introduce here is the space-borne remote sensing. One of the most commonly used remote sensing or like satellite remote sensing products in the field of urban climate is the so-called MODIS, which is the moderate resolution imaging spectral radiometer, or simply MODIS, and which can provide spatially continuous measurements of land-surface temperature or other urban environmental variables, such as vegetation distribution or like water body distribution or any other kind of urban climate-related variables. Okay, any questions so far?
Hi, Chenhao. Yeah, sorry, I missed a part of the talk. I was wondering if you had any thought about the low-cost sensors, and if you talked about it, I might have missed it, but if you not, could you comment on this a little bit, please?
Yeah, sure. So if our focus, I think I had a comparison somewhere out here. Yes. So if our focus is, for example, we want to collaborate with some, citizen scientists, or if we just want to get a two-dimensional distribution of some, temperature across the entire city, we can of course use this low-cost sensor. Or like some general, we do not need to ensure the high quality of air pollution measurements. We can use low-cost sensor to get a two-dimensional distribution. But if our purpose is for research, we want to publish paper, we want to validate the measurements against our model, we must need some high quality, high cost sensors. And this is actually a real situation we're facing in one of our ongoing projects. We're trying to use these low cost sensors to cross-validate the high quality LiDAR sensor to measure the methane concentration. And this, because of the cost difference, these different sensors will have different detect limit. For example, we know that methane concentration in the atmosphere is around 2000 ppb or 2 ppm. And if you're using this low cost sensor, the sensitivity is around like 1 ppm. Basically, every time you measure a signal, it is actually a high peak of methane emission. But if we're using LiDAR, we can detect several like tons of change in methane concentration in terms of ppb. So it's much more sensitive than these low cost sensors. So it totally depends on what you're trying to do with these sensors.
Okay. Yeah. Thank you.
Any other questions?
I have one question.
Mm-hmm.
Yeah, actually two questions. First one is talking about for example, looks like, give me the feeling most of the sensors you are using for the urban energy balance is in the below the surface layer, just inside the surface layer.
Right.
Yeah. My question will be focused on when we combine the simulation and the sensor technique together, because when I run in the larger simulation models, and give me the feeling people give very big domains. For example, if we are talking about the convective boundary layer or something, looks like the calculation domain we are using 2 kilometers or even larger domain. and give me the feeling sensor is very close to the wall, just like that, maybe 100 or 200 meters.
Right.
So my question will be, based on your experience, if we want to test the compare the result from simulation and the experiment. So do you think the domain size is very important, or it's
Yes.
it's
So if
fine?
you want to like validate the entire atmospheric boundary layer simulation, you might need to use some like profiling data, like the profiling data sets, like based on airborne measurements or based on LiDAR or radar measurements, and instead of just using the near surface stations.
Oh,
yeah,
nice. Okay, thank you.
Okay, let's get going. So where were we? Okay, so let's move on to the second part of today's lecture, which is urban physical modeling. So physical model is essentially a simplified surrogate of a real world system. Sometimes it is also called hardware model or scale model. And I will use these three terms interchangeably in my following slides. And in this physical model, we are, representing these buildings and other urban elements as scaled or simplified geometry. For example, this is a scale model of the real downtown Oklahoma City in a wind tunnel in Germany. And this is wind tunnel experiment following the 2003 joint 2003 urban field campaign. And you can see that we have this replicates of buildings and this church as well. Physical modeling actually requires the similarity, where sometimes we call similitude between the model and the realistic system it is representing. In general, we have three different types of similarities. We have geometric similarity, dynamic similarity, which is sort of related to airflow, and also thermal similarity, which is related to heat transfer. And of course, a perfect physical model should properly replicate the fluxes of mass, flux of momentum, and also energy fluxes. But in reality, it is really hard to achieve all these three different similitudes or similarities. So in practice, we will always try to ensure similarity in one or two of these properties. Sometimes we only ensure, we have energy similarity or, mass similarity. Sometimes we have, mass or momentum similarity. So the first similarity, geometric similarity, is the most basic form. It actually ensures that we have consistently scaled length dimensions and also angles. What I'm showing here is a scale model of Pudong district in Shanghai in a wind tunnel. The figure on the right here is the figure on the left here is the actual scale model within this wind tunnel. And this figure here is the real building configuration. As you can see, that most of the geometric characteristics of the highest three buildings are retained, including their spatial configuration and their relative relationship with the surrounding high-rise buildings. This kind of geometric similarity is very, very important if we want to study the radiative exchanges or shadow patterns of different urban geometries. So the second one, dynamic similarity, requires the model to mimic the airflow or the momentum transfer. A rule of thumb is that we need to make sure the flow in the. Oh, I think someone is in the waiting room. Okay, very good. So where are we? Okay, so a rule of thumb is that we need to make sure the flow in a wind tunnel should have similar Reynolds number as in the real atmosphere. So if you think about how Reynolds number is defined, if we reduce the length scale L in this equation, and denominator here is viscosity, which is constant basically, we must have a much higher wind velocity so that the Reynolds number is close to what we have in real atmosphere, which is about 10 to the power of 7. And this is also why it is better to have a bigger scale model in wind tunnel so that we don't need to increase the wind speed so much. So the last one is thermal similarity, which aims to mimic heat transfer or like temperature changes of a surface or a material. This one is important if we want to measure temperature or heat exchanges. But the materials sometimes we use can introduce large biases. For example, if you ever want to simulate the tree cooling effect, and you cannot simply use this plastic materials or like porous materials. Like this one is a fake Christmas tree set up on a rooftop of ASU campus, and because they don't transpire, right? They do not represent the realistic biophysical processes associated with vegetation. Also, the size of the building materials we're using sometimes are also problematic because they cannot nicely reproduce the actual thermal mass of buildings. So as you can see from the examples I just showed, these skill models can be both indoor and outdoor, right? So this one is indoor within a wind tunnel, and this one is outdoor exposed to the real weather. So the major difference is, of course, indoor models only experience some controlled or designed environmental conditions, while outdoor models experience actual weather conditions and can really interact with the real atmosphere. So let's first talk about some examples of indoor models. So a helidon is a typical lab model that we can use to simulate the direct and diffuse solar radiation. This instrument can actually adjust the location and strength of radiation. So here is a helidon in Cardiff University in UK. And if you take a look at this black track over here, so it actually has a moving light source which can mimic the direct solar radiation, and all these light bulbs surrounding the entire hemisphere, upper hemisphere, can simulate the diffuse solar radiation. And the location and strength of the radiation can both be adjusted so that we can reasonably reproduce the actual radiation on Earth, and they can also reproduce the shadow patterns cast by all these different buildings. And we can also use this helidon to study, for example, the solar axis of a building or a specific surface. And also we can study the solar exposure of a solar panel in some complex urban environment. Think about if we ever want to put a solar panel on the ground surface surrounded by a bunch of high-rise buildings, we must consider the potential exposure of the solar panel to the solar radiation. Researchers have also designed some different models to simulate urban temperature. So this is one of the most classic lab models designed at University of British Columbia. The researchers were trying to understand how these three-dimensional urban geometry of an urban neighborhood could really influence the cooling rate in an urban park, which is in the center of this picture. They use these wooden blocks to represent surrounding buildings, and this foam rubber to represent trees. Apparently, this one only preserved the geometric similarity, right? We do not have this dynamic similarity or thermal similarity. So as for lab models for airflow related studies, the most commonly used infrastructure is, of course, the wind tunnel. We also have, of course, a water tunnel, which can have different flow speed. And this wind tunnel is more like a giant pipe, if you ever seen that in person. So it can either recirculate the air within the system, just like what I'm showing here, this blue one, or it can draw or push the air from the room into the test section. And in the test section, researchers will often put a scale model of a building or a part of the urban neighborhood. And because in this case we have wind constantly blowing from this direction toward the test section, we cannot really alter the wind direction. Instead, the researchers can design this turntable to adjust the orientation of the urban neighborhood to mimic the different wind directions. So here is another illustration of the structure in a typical wind tunnel. In the inlet part, we have these giant turbulent generators to generate proper turbulent profiles. We also have a bunch of roughness elements to create a nice wind profile approaching the test section. But one downside of these experiments is that it is really hard to reproduce the Coriolis force. We cannot, really reproduce the, large-scale weather events that are affected by the Coriolis force. So these wind tunnel measurements are also widely used in to study pollution dispersion within the urban environments. Here is one example showing an experiment done by the University of Karlsruhe. They were trying to understand, the impact of the source heights on pollution dispersion in an industrial urban area. You can see a bunch of, factories over here. Apparently, as you reduce the emission emission source from the inertial sublayer, deep down into the urban canopy layer, the dispersion will be much more, spread out instead of a nice plume shape like this one in the inertial sublayer. Okay, let's move on to our outdoor models part. As I mentioned earlier, outdoor models are exposed to real weather, so we do now need to simulate the radiation. Here, in the small 1/13th, I think, outdoor scale model, researchers are, using an array of concrete blocks to represent cubical buildings. And remember, I mentioned earlier that it's usually hard to achieve thermal similitude or thermal similarity. But researchers have come up with some solutions for this. For example, we may install some small water tanks into the scale model buildings so that they can more realistically respond to heat transfer. And outdoor models are also used for urban wind and turbulence studies. Researchers in Japan have created a very neat physical model called Cosmo, and they use this more than 500 cubical buildings to simulate the influence of buildings on both airflow and precipitation. And these cubes are much larger than what I showed in one of the previous slides. This one here, this one here. So each of these is about 1.5 meters tall and almost the height of a pedestrian. And recently, another group of researchers in China also created another scale model platform called So Much in Guangzhou, China. They use several rows of these concrete blocks to create straight canyons with different canyon aspect ratio, which is the ratio of building height to canyon width. They also have live plants to simulate the impact of straight trees on wind, on temperature, and also on pollution dispersion. Okay, any questions before we move on to our last part of numerical simulations? We have about 30 minutes left. If not, let's move on to our numerical modeling. So numerical models basically are models that can simulate the real world phenomena using a set of mathematical or physics-based equations that can link different atmospheric properties, for example, temperature, humidity, with processes such as sensible heat flux, latent heat flux, or the heat transfer among different materials. So in every model we design, we always need some governing equation so that we can, describe the system in a mathematical and solvable way. So in numerical modeling for, atmospheric related studies, we must consider, conservation of momentum equation, mass conservation equation, energy conservation equation. We also need to define some proper surface boundary conditions, and also we need to have this numerical discretization. And let's go into detail for each of these governing equations. So as some of these equations have already covered in previous lectures, I will briefly go through these equations only very briefly. So the first equation is this momentum conservation equation. It is a result of the Newton's second law. Basically describe the total derivative of the wind velocity in each direction is equal to the sum of all forces. We have a Coriolis force, pressure gradient force, due to the pressure difference, and so also due to the gravitational force and also frictional force. We have drag force and form force. Form drag and skin drag. And so this is the principle of momentum conservation. And we also have, the mass conservation equation. If you consider, a problem domain as a system, the change rate of a mass, within this system should always be equal to the inputs minus outputs. So on the right-hand side, we have this net mass flux, but we also have other, the other sink terms and source terms, such as this rate of emission and rate of decay. So if we further assume that air is incompressible, which means we have constant density and there's no emission or decay, basically we assume E and D are both equal to 0. We can have this divergence of flow velocity is equal to 0. This is how we link together wind velocity in 3 different directions. And the third governing equation is the energy conservation equation. Here we are using the first law of thermodynamics. Energy can neither be created nor destroyed. So we have the change of internal energy equal to the change of energy due to compression or expansion, plus the change of energy due to addition or subtraction of heat, basically the heat exchange between the system and the surrounding environment. So the last one is just the equation of state or ideal gas law, which determine the state of an air parcel in terms of its pressure, volume, and temperature or density. R here is the gas constant, of course. So using these 4 different equations, and we can actually solve for some common variables within these 4 equations. For example, pressure, temperature, velocity, and other different variables. Okay, we also need to define the boundary conditions of the model, right? For the sake of time, I will only mention the lower boundary here, which is essentially urban surface. If our model is an urban climate model, we also need to properly represent the aerodynamic properties, radiative properties, and also thermal properties of this urban surface. We also need to define the surface energy balance and surface mass balance, such as water balance, and sometimes we can have this a mixture of both. So the last one is numerical discretization, which is also sort of covered in previous lecture, especially Dr. Zhu's lecture. And different from reality, numerical models require some discrete forms in both space and time. For continuous space, we need to convert it to discrete cells and solve for equations in each cell, just like this one. Here, these 3 figures show some common model grid configuration for urban airflow simulation. So they can be either this, uniform, this uniform with identical size for each cell, or they can also have different sizes for these irregular shaped cells. They are usually much smaller when we are closer to the surface of the roughness elements. But they will become much bigger when we move away from this roughness elements, because the environment is more homogeneous. We can use this technique to reduce the computational cost. So these discrete cells directly determine the model's spatial resolution. In general, commonly used urban climate models often have commonly used global or regional climate models often have very coarse spatial resolution. Most of them are at 1 degree or even coarser. This figure actually shows the continuous improvement of model resolution across 4 different IPCC climate change assessment reports. So this is the first one, second one, third one, and AR4 assessment report, fourth assessment report. So as we improve the spatial resolution over time, we can actually have more detailed representation of coastline and topographical variations across entire Europe. However, in most global climate models, urban areas are still largely simplified as an impervious surface only, which is sometimes called a SLAP model. Although we can use the so-called urban canopy models in many mesoscale models, the representation can still be largely limited by their spatial resolution. For example, here is a comparison of urban grids into continental scale wharf simulations over Oklahoma City. So this one is from another paper, but this one is from my earlier work. So this one actually used 20-kilometer resolution, but this one in my work used 5-kilometer resolution. Apparently, the 5-kilometer one has more detail, which at least capture the shape of Oklahoma City and Tulsa, which is quite different from what we have in this 20-kilometer resolution simulation. Oh, one thing I do want to mention that we also need to discretize the continuous time domain. So we need to separate the continuous time into the discrete intervals, which determines the temporal resolution or time step of our model. So urban climate models also have different spatial scales and dimensions. For example, we can have this either one dimensional model or a so-called single column model that only consider the vertical exchanges between the ground surface and the atmosphere. We also have these two-dimensional models that assume in the spanwise direction the buildings are infinitely long, which is sort of a reasonable assumption, especially for densely populated urban environments. And this figure this figure is actually from a paper Dr. Lee and I worked together several years ago. So we are trying to understand the influence of urban trees on the distribution of air pollutants. So of course, the most sophisticated one is this three-dimensional model, but this is also much more computationally expensive when compared to this one-dimensional single column or this two-dimensional urban canyon representation. So here is another illustration about how we can numerically represent the urban surface. We can have this, two-dimensional SLAC model, and we can also have this two-dimensional street canyon representation, and also the two three-dimensional urban surface models. In addition to these different surface representation methods, we can also model different physical and biophysical processes within the urban environment. Like, we can model grass, we can model street trees, and we can, reproduce the building energy use, and we can mimic the urban irrigation and even, some anthropogenic heat emissions. But a common approach in urban climate field is that models usually only focus on either airflow or surface energy fluxes. If you, are dealing with CFD, usually you do not need to consider, these very sophisticated surface energy fluxes. They are much simplified. But if your focus is on surface energy fluxes, you will usually use a highly simplified airflow or like a wind profile or like turbulent representation. So in practice, we often switch off, some certain physical or biophysical processes to better isolate it, the effects of some certain processes. This is also helpful if we want to do some attribution studies. Of course, we should use different models for processes at different spatial scales, right? For micro scale and local scale urban climate models, the focus is basically on the roughness sublayer or and the urban canopy layer. Based on the modeled physical processes, there are three major categories of micro scale or local scale urban climate models. So these momentum related models are used to simulate the airflow or turbulence. Energy fluxes models are used to resolve the surface energy balance, while the mass balance models are used to study water balance or air quality or any other kind of mass related studies. So for models focusing on airflow and turbulence, we use the so-called computational fluid dynamics model or CFD models. Depends on how detailed a model can solve for all governing equations. We have the Reynolds average number Stokes equation model, LES, which is large area simulation, or DNS, which is direct numerical simulation. So as you can see in these two graphs, as we move from Reynolds to LES or even to DNS, which I'm not showing here, we will be able to resolve more finer scale eddies and improve the model fidelity of the reality. But the computational cost is also drastically increasing if we move from Reynolds to DNS. So for reference, Reynolds only simulate the average status of the turbulent flow, as Dr. Lee mentioned in our first two lectures. So one thing I do want to mention that is that although historically these CFD models for urban climate studies often have relatively simple geometry, for example, the two-dimensional representation of urban street canyon, but with the development of computational power, we are now able to model the entire urban neighborhood or even the entire city using CFD models. So there's a large advancement in this field. So for models focusing on surface energy balance, we also sometimes call them land surface model. So these similarly has different spatial dimensions, right? From this one-dimensional to two-dimensional multifaceted, and even to the three-dimensional complex urban environment. So in the following 3 slides, I will briefly introduce a two-dimensional urban canopy model we have developed, so that you can have a better understanding of how researchers usually progressively improve the urban climate model to capture more physical and biophysical processes within cities. So the model we developed is a so-called Arizona State University single-layer urban canopy model, or ASLUM, luminous illumination. So this model was first developed in more than 10 years ago. The first version of this model only has some basic features, such as we can simulate the urban canopy layer heat exchange between different urban facets. We can also have this subsurface heterogeneity, which means we can use different materials over the same surface. And we also simulate some basic hydrological processes, such as evapotranspiration and infiltration. And later on, we developed the second version, focusing more on the interactions between human and urban environment. This version has some new features, such as green roof module and ground vegetation module. And we also have this urban irrigation module and anthropogenic heat. We can model both anthropogenic sensible heat flux and anthropogenic latent heat flux. But this is still rather simplified, right? If you take a look at this sketch over here, because we are missing trees. So in the third version, we added 3 trees and tried to simulate the shading effect, evapotranspiration of tree canopy, and root water uptake, and also canopy transmittance, because the foliage variations across different seasons can influence the radiative exchange between the tree canopy and the surrounding environment. So we are still continuously developing this model currently. The newest version also has carbon exchanges. My group is also developing a multi-parameterization version of this model to better simulate hydrological processes. My student Yuqi is leading this part. But we're not alone. There are also some research groups developing similar urban canopy models. So in order to understand the challenges in urban climate simulations, the urban climate research community has conducted 2 rounds of urban land surface model intercomparison projects. The first one was done in about 15 or 14 years ago, which includes 32 urban land surface model or urban climate models, and did their validation or evaluation in 2 sites, one in Canada, one in Australia. For the sake of time, I will not go into detail, but the main conclusion of the first intercomparison project is that vegetation was poorly represented back in most of the models back at that time. And one interesting finding is that more complex models do not necessarily perform better than simpler models. So we might need some models with intermediate complexity, so that we can both capture some essential physical and biophysical processes while saving our computational cost. So in about 3 years ago, we did the second round of urban climate model intercomparison project. This one is led by UK's Met Office and University of Reading in UK, of course. So the results of phase 1 comparison was just published in this QJ RMS journal. And this project includes 30 models, urban land surface models, of course. And in phase 1, we have this single site evaluation in Australia. In phase 2, we are validating different models across 20 cities with different background climates. So, and this time we see some substantial improvements in urban energy flux modeling, especially the vegetation representation. For example, several models now have the capacity to model street trees, which was not really possible in the first intercomparison project. But these land surface models still only take large-scale weather data as the input to force the modeling at finer scale. But what if we want to know the impacts of urban surfaces on broader scale weather and climate systems? We need to use some mesoscale model or even global scale models. So a commonly used approach is to couple a mesoscale model with a suitable local or a microscale urban climate model. So we also use the so-called coupling approach to consider the interactions between these coarse resolution mesoscale models and the finer resolution urban climate models. So basically, the mesoscale models will be able to provide upper boundary conditions to force this local scale model. Well, when we solve for this local scale model, it will also provide lower boundary conditions as an input into the mesoscale model to change some conditions. So we have this, two-way coupling. But sometimes, if you want to speed up the calculation, you might, turn off this, feedback from local scale to mesoscale. You just consider this one-way coupling. But for the one I'm showing here, this is two-way coupling. So another characteristic of mesoscale model is the tiling approach, because the numerical cell is often very coarse, right? Which can have both, rural and urban surface within each cell. So instead of just using an urban climate model to simulate the entire grid, we combine the results of an urban climate model and the natural land surface model. In this way, we separate model the urban fraction and non-urban fraction and calculate the weighted average as an output from this numerical cell and get back to the SFR grid cell. But there are always some challenges for this kind of mesoscale urban models, especially when the resolution is coarse. So think about what we are doing when we validate the simulated variables. We're validating, this, 20 kilometer resolution, or even 1 degree resolution grid cell versus a point scale station measurements, right? This scale mismatch often creates a lot of uncertainties, and it is really hard to really tell whether the model is doing great or not. Okay, so the last type of models I want to introduce is the so-called empirical models, or sometimes it is called practical models, which is fairly easy. It's basically a statistical relationship between some variables. And for example, this one I'm showing here is a regression model we built between the sensible heat flux and the convective heat transfer. The surface and adjacent air temperature difference. So we are building a linear correlation between these two variables, and the coefficient within this regression equation is the so-called convective heat transfer coefficient. We can use this relationship to determine this HC term. So these kind of empirical models can be highly practical if we want to do some quick predictions or like some rapid simulations. But this, of course, is largely constrained by the data we use to train the regression or statistical model. We also actually have similar issues for other data-driven models, such as machine learning-based models. They are really good for interpolation if you have the condition or measurements for on both sides of the spectrum, and we can easily do interpolation, and the results will be also very accurate. But if you ever want to do extrapolation, to predict some conditions that we have never observed in reality, this can be problematic. So this, empirical models are always good for interpolation instead of extrapolation. Okay, so this is my last slide. I think we still have some time for questions. So any questions for modeling part or any parts I introduced into this lecture? I know it's very quick because I just want to cover a lot of things, and so that you can think about it later after our lecture. We have recording online, so you will have time to rewatch it.
Thank you, Chenghao. Yeah, I have a quick question. So, for example, if a graduate student or someone who has little experience running these urban climate models, what will be a rough estimate of how long it takes for them to, get started?
That's a good question. I think it depends on what kind of model you're trying to learn, right?
Oh yeah, of course.
If your goal is to learn this one, I think this one will only cost you like 1 hour or even less, right? But if you are trying to learn urban canopy model, especially the online version within the Wolf model, it might take you about like 1 week. But if you want to modify really modify the code within the urban canopy model, it would take even longer. And if your goal is to learn the CFD models, it will. I think you have more experience. Can you give me one explanation about all of it?
Yeah, and I also wonder how much of these in the inter-comparison projects you have done with the urban canopy models, around the world, how many of these models are, open source and open, sort of open data, and is this a trend that, for example, that the urban climate research community that's also being interested in?
That's a great question. I think among the 30 models we have in this project, I would say about half of them are open sourced, or even 1/4 are semi-open sourced. If you ask the leading scientists, they will kindly provide you the code. But there are some still internally developed codes. But I do want to mention that among these 30 urban land surface models, there are a bunch of models that have been commonly used in the field, even in WRF and in other mesoscale models like NOAA LSM, land surface model, I mean. And is definitely a trend. And this is also something we are trying to resolve for our model. So currently our model is not open source, but we are trying to incorporate our tree model into the online WRF model. This will be happening very soon this summer. So I would say this is definitely the trend. We don't really take the time to reinvent the wheel, right?
I have one question.
Mm-hmm.
Yeah, about the how to use the model. For example, here, you and the colleagues develop a urban kind of model, as you show the figure here.
Mm-hmm.
So my question is how to do how this model is used, or what's the input and output of this model, and what can we use this model to prediction?
So for these urban canopy models, the input are usually from a nearby flux tower with measurements well above the urban canopy layer. Or if we do not really have a flux tower, we can use some coarse resolution reanalysis data like ERA5 to approximate the general weather conditions around this neighborhood. So that's the input of the model. But usually we will need a flux tower or even a weather station right within this urban neighborhood so that we can validate the performance of our model.
So this model can be used for predict the energy balance, or what?
Yes. So this is what we did in this one. So we have 50-year observation data in 20 cities, and we were given only the input, the forcing data, partially derived from flux tower, partially derived from ERA5 when we have observational gaps. And we use this data to force different urban land surface models, and these different models can produce the prediction of sensor heat flux, latent heat flux, ground heat flux, and different radiation components. And then, the leaders in this project will use our outcomes to validate the performance, to evaluate the performance of different models in these predictions.
Nice. Okay, thanks.
Any other questions?
Okay. So if any other questions? So if we do not have more questions, then we have concluded the first crash course for this year. Thank you, Dr. Wang, Dr. Zhu, for all the great lectures, and thank you everyone for the participation. And so we'll update all the recordings and the slides and the materials in the link that we sent out in the email list. Okay, great. Let me stop recording.